Hello there, and welcome to The Sleeping Scientist. I'm so glad you found your way here. Maybe you had a long day, or maybe you're the kind of person who likes falling asleep to deep thoughts and cosmic mysteries rather than counting sheep. Either way, tonight's journey is for you. You've got nothing to do but rest. Let your mind relax, your breathing slow, and your body grow light as if gravity itself has softened. Because tonight, we aren't simply stargazing, we're drifting through galaxies. Let's begin. The first galaxies formed in near total darkness. No stars yet existed to light them, just hydrogen gas collapsing under its own weight, heating up, glowing faintly in infrared wavelengths we'd never see with human eyes. This happened roughly 13 billion years ago, and we're only now learning how it worked. What's strange is that these ancient structures weren't chaotic. They followed patterns, rules written into the fabric of space-time itself. Dark matter created invisible scaffolding, gravity pulled gas into streams, and somewhere in that process, the first stars ignited. Not with a bang, but slowly, like embers catching in a cold universe. The earliest galaxies were smaller than you'd expect. Some contained only a few million stars. Tiny compared to the Milky Way's 100 billion. They formed in clumps, merging together over eons, building larger structures piece by piece. Each collision added mass, stirred gas clouds, triggered new waves of star formation. The universe wasn't born organized. It learned to organize itself. Here's what nobody tells you about early galaxy formation. It was inefficient. Most of the gas never became stars. It heated up, got blown away by stellar winds, or simply stayed suspended in halos around the galaxies. Only about 10% of available material actually condensed into suns. The rest drifted, waiting, sometimes for billions of years. The first stars were nothing like our sun. They formed from pure hydrogen and helium. No heavier elements yet existed. This made them massive, hundreds of times the sun's mass, burning blue-white and dying quickly. Their lifespans measured in millions of years, not billions. When they exploded, they seeded space with carbon, oxygen, iron. Every element heavier than helium in your body came from stars like these, dying before Earth even existed. Dark matter shaped everything, but remained invisible. We still don't know what it's made of. We just know it's there because of how it bends light and pulls on visible matter. In the early universe, dark matter created gravitational wells where normal matter accumulated. Think of it as the mold that gives galaxies their form, except the mold itself can't be seen or touched. Early galaxies glowed primarily in ultraviolet light. The young massive stars pumped out high-energy radiation that ionized surrounding gas, creating glowing nebulae. This period, called the Ionization epoch, lasted hundreds of millions of years. Before it, the universe was dark and neutral. After it, space became transparent, allowing light to travel freely across cosmic distances. The James Webb Space Telescope recently captured images of galaxies from just 300 million years after the Big Bang. They appear as red smudges, their light stretched by the expansion of space itself. What was once ultraviolet has been redshifted into infrared. We're seeing these galaxies not as they are, but as they were, frozen in time by the speed of light. Distance in space equals distance in time. When astronomers look at a galaxy 13 billion light years away, they're seeing light that left 13 billion years ago. That galaxy has moved, evolved, possibly merged with others by now. We'll never see its current state. The farther out we look, the further back we see, until we reach a wall. Not a physical barrier, but a temporal one. The moment when the universe became transparent. Before that transparency, light couldn't travel. The universe was too hot, too dense. Photons scattered off free electrons constantly, unable to move more than a short distance before colliding again. Then atoms formed, electrons bonded to nuclei, and suddenly light had a clear path. The cosmic microwave background radiation we detect today is the afterglow of that moment, stretched and cooled by billions of years of expansion. Early galaxies weren't alone. They existed in clusters, connected by filaments of gas and dark matter. These cosmic webs stretched across millions of light years, creating the large-scale structure we still observe today. Galaxies formed where filaments intersected, in regions of higher density. The voids between filaments remained mostly empty, vast, dark spaces containing almost nothing. Supermassive black holes appeared early, too early by our understanding. Quasars, powered by black holes billions of times the Sun's mass, existed less than 1 billion years after the Big Bang. How they grew so large so quickly remains a mystery. Normal black hole growth, fed by infalling matter, shouldn't happen that fast. Either they started with massive seeds, or they grew through processes we haven't identified yet. The metallicity of early galaxies was low. Metallicity, in astronomy, refers to elements heavier than hydrogen and helium. First-generation galaxies had almost none. Second-generation galaxies had traces. Each successive generation incorporated more heavy elements produced by dying stars from previous generations. Our Sun is a third or fourth generation star, rich in elements forged in ancient stellar furnaces. Galaxy rotation curves reveal dark matter's presence. When astronomers measured how fast stars orbit galaxy centers, the speeds didn't match predictions based on visible matter alone. Stars on the outer edges moved too quickly. They should have been flung into space. The only explanation: invisible mass creating additional gravitational pull. This discovery in the 1970s revolutionized cosmology. Early galaxies underwent rapid star formation, creating stellar populations in bursts rather than steadily. These starburst galaxies converted gas into stars at rates hundreds of times faster than modern galaxies. The process couldn't last. They'd exhaust their fuel within tens of millions of years. But during those bursts, they outshone everything around them. Gravitational lensing lets us see even earlier galaxies. Massive galaxy clusters warp space-time, bending light from objects behind them. This creates magnified, distorted images of distant galaxies we couldn't otherwise detect. Einstein predicted this effect in 1915. We're now using it to peer deeper into cosmic history than our telescopes could manage alone. The first galaxies may have formed even earlier than current observations suggest. We found candidates at redshifts indicating they existed just 200 million years after the Big Bang. Confirming these requires careful analysis, distinguishing genuine high redshift galaxies from closer objects that mimic their signatures. Each new discovery pushes back the timeline of when structure first emerged. Dust formed surprisingly quickly in early galaxies. We've detected dust signatures in galaxies less than 700 million years old. Dust comes from dying stars, which need time to evolve and explode. Finding it so early suggests either stars formed and died faster than expected, or dust production mechanisms were more efficient in the early universe. The temperature of the universe has been dropping since the Big Bang. In the first moments, temperatures exceeded trillions of degrees. By the time the first galaxies formed, it had cooled to thousands of degrees in some regions. Today, the average temperature of intergalactic space hovers around 3 Kelvin, just above absolute zero. The universe grows colder as it expands. Proto-galaxies merged constantly in the early universe. Collisions weren't rare events, but common occurrences. Each merger triggered new star formation, disrupted existing structures, and mixed different populations of stars. The Milky Way itself likely formed through dozens or hundreds of such mergers over billions of years. The Hubble Ultra Deep Field revealed thousands of early galaxies in a patch of sky no larger than a grain of sand held at arm's length. This tiny section of space, observed for days to capture faint light, showed galaxies in every direction, at every distance. The universe wasn't just full of stars, it was full of galaxies, each containing billions of stars. Early galaxies had irregular shapes. The neat spirals and ellipticals we see today developed over time. Young galaxies were clumpy, asymmetric, still settling into stable configurations. Tidal forces from neighbors, internal dynamics, and ongoing mergers kept them in flux. Order emerged gradually from initial chaos. The Lyman alpha forest provides clues about the early universe. This series of absorption lines in quasar spectra reveals intervening clouds of hydrogen gas between us and the quasar. By analyzing these lines, astronomers map the distribution of matter in the early universe, tracking how it clumped and evolved. Cosmic dawn refers to the moment when the first stars ignited. Before this, the universe had been dark for hundreds of millions of years following the Big Bang. The formation of those initial stars marked a fundamental transition from a simple universe of hydrogen and helium to one where chemistry, complexity, and eventually life became possible. We're still discovering how galaxies transition from irregular to spiral. The process involves settling gas into rotating disks, forming spiral density waves, and establishing stable structures. Environmental factors matter too. Isolated galaxies evolve differently than those in clusters. The details remain under investigation, each new observation refining our understanding. The universe was once much smaller, denser, and hotter. Galaxies that now sit billions of light years apart were once close together. Space itself has expanded, carrying galaxies along with it. They're not moving through space so much as space is growing between them. This expansion is accelerating, driven by dark energy, another mystery we haven't solved. Early galaxy studies reveal how structure emerged from near uniformity, how the first stars lit the darkness, how black holes grew to enormous sizes, and how the cosmic web took shape. Each new discovery raises more questions than it answers. We thought finding the first galaxies would close the book on cosmic origins. Instead, it opened volumes we hadn't anticipated. The James Webb Space Telescope keeps pushing those boundaries, revealing galaxies that shouldn't exist according to our models, structures that form too quickly, stars that burn too brightly for their age. Consider what we're actually seeing when we observe these distant objects. Light left them over 13 billion years ago. It's traveled through expanding space, stretched into infrared wavelengths, dodged countless obstacles. By the time it reaches our instruments, it's faint, reddened, ancient. Yet from those tired photons, we reconstruct entire histories. We measure compositions, temperatures, sizes, masses. We infer how stars lived and died in those systems. The precision is remarkable, but so are the uncertainties. Some early galaxies appear remarkably mature. They have well-defined structures, established stellar populations, chemical signatures suggesting multiple generations of stars. How did they organize so quickly? Standard formation models suggest gradual assembly, small structures merging into larger ones over hundreds of millions of years. But we're seeing organized systems much earlier than that timeline allows. Either something accelerated the process, or our understanding of gravity and gas dynamics needs revision. The role of dark matter complicates everything. We can't see it directly, but its gravitational effects shape how normal matter behaves. Dark matter formed the scaffolding upon which galaxies assembled. It clumped first, creating potential wells where gas could accumulate and collapse into stars. Without dark matter, galaxies wouldn't exist. But we still don't know what dark matter is. We infer its presence, map its distribution, simulate its behavior. The substance itself remains invisible, detectable only through its influence on visible matter. Early black holes present another puzzle. Quasars powered by supermassive black holes appear when the universe was less than 1 billion years old. These black holes contain millions or billions of solar masses. Growing that massive in such a short time challenges our models of black hole formation and growth. Standard accretion processes, where black holes pull in surrounding matter, can't build mass quickly enough. Either they started much larger than we thought possible, or they grew through mechanisms we haven't identified. Some theories propose direct collapse of massive gas clouds into black holes, bypassing the stellar phase entirely. Others suggest mergers happened more frequently than expected, allowing rapid mass accumulation. The chemical evolution of early galaxies proceeds differently than anticipated. Heavy elements form inside stars and disperse when those stars explode. Finding significant amounts of carbon, oxygen, and iron in very young galaxies means stars formed, evolved, and died remarkably quickly. The first generation, composed purely of hydrogen and helium, must have been massive, short-lived, and explosive. Their deaths seeded the next generation with metals, enabling more complex chemistry and eventually planetary systems capable of supporting life. Observations reveal surprising diversity among early galaxies. Some are compact and bright, others extended and faint. Some show vigorous star formation, others appear quiescent. This variety suggests multiple formation pathways, different environmental conditions, varied merger histories. No single template explains all early galaxies. Each represents a unique outcome of initial conditions and subsequent evolution. Gravitational lensing amplifies our view of the distant universe. Massive galaxy clusters bend light from objects behind them, magnifying and brightening those background sources. This natural telescope allows us to see galaxies too faint or small to detect otherwise. Some of the earliest known galaxies were discovered this way, their light boosted by foreground lenses. The technique reveals populations of small, faint galaxies that might constitute the building blocks of larger systems. Ionization transformed the universe. After the cosmic dark ages, when the first stars ignited, their ultraviolet radiation began ionizing surrounding hydrogen. This process spread outward from each source, creating bubbles of ionized gas that eventually merged into a fully ionized medium. Ionization wasn't instantaneous or uniform. It proceeded in patches over hundreds of millions of years, influenced by the distribution of early galaxies and the density of intergalactic gas. Mapping this process helps us understand how the first light sources altered their environment. Star formation rates in early galaxies were extraordinary. Some converted gas into stars hundreds of times faster than the Milky Way does today. This furious activity couldn't last indefinitely. Eventually, gas supplies depleted, supernovae expelled material, or active galactic nuclei heated the gas and prevented further collapse. Understanding what regulated star formation in young galaxies helps explain why modern galaxies form stars more leisurely. The cosmic web's influence extended even to the earliest structures. Galaxies didn't form in isolation, but along filaments where dark matter and gas concentrated. These cosmic highways fed galaxies with fresh material, enabling continued growth. Galaxies in denser regions experienced more interactions, triggering mergers and starbursts. Those in voids evolved more peacefully. Environmental effects mattered from the beginning, shaping trajectories that persisted for billions of years. Metallicity gradients tell stories of galactic assembly. In many galaxies, the central regions contain more heavy elements than the outskirts. This gradient reflects inside-out growth, where the core formed first and enriched quickly, while outer regions assembled later from less processed material. Early galaxies showed different patterns, sometimes with surprisingly uniform compositions or inverted gradients. These signatures reveal how gas flowed, where stars formed, and how stellar feedback redistributed metals. Dust obscuration complicates observations of early galaxies. Dust absorbs ultraviolet and visible light, re-radiating it in infrared wavelengths. Heavily obscured galaxies might appear faint optically, but bright in infrared. Missing these sources biases our understanding of star formation rates and galaxy populations. Webb's infrared sensitivity helps, but we still struggle to account for all obscured systems. Some early star formation might remain hidden even from our best instruments. Galaxy morphologies evolved over cosmic time. The fraction of spiral galaxies increases in more recent epochs, while irregular and peculiar galaxies dominate earlier eras. This shift reflects the universe settling down, mergers becoming less frequent, and stable structures having time to develop. The transition wasn't sharp but gradual, a continuous evolution from chaos to order. Supermassive black holes and galaxies co-evolved. Their masses correlate in the local universe, suggesting linked growth. But the relationship's origin remains unclear. Did black holes form first and regulate galaxy growth through feedback? Did galaxies form first and feed central black holes? Or did both grow simultaneously through processes we haven't identified? Early observations show black holes sometimes outpacing their host galaxies, sometimes lagging behind. The relationship might have been messier initially, only settling into the tight correlation we observe nearby. Cosmic variance challenges conclusions drawn from small survey areas. The universe isn't perfectly uniform. Large-scale structures create regions denser or emptier than average. Observing a small patch might sample an overdensity, leading to overestimates of typical galaxy abundance. Or it might hit a void, suggesting galaxies were rarer than they actually were. Only by surveying large areas can we average out these fluctuations and determine true cosmic means. Early studies based on limited fields sometimes reached contradictory conclusions because they sampled different environments. The first billion years witnessed extraordinary transformations. Neutral hydrogen ionized, the first metals dispersed, black holes grew to supermassive scales, and galaxies assembled from scattered gas clouds. The universe evolved from a simple post-Big Bang state to a complex, structured cosmos. Understanding this period reveals how the ingredients for everything we see today came together, how the conditions for life emerged, how the universe transitioned from its initial simplicity to its current richness. Simulations help bridge observations and theory. Computational models follow dark matter's gravitational collapse, gas cooling and fragmentation, star formation and feedback, black hole growth and influence. By comparing simulated galaxies to observed ones, astronomers test physical assumptions and refine models. Discrepancies highlight missing physics or incorrect parameters. When simulations match observations, they provide insights into processes we can't directly observe, revealing the causal chains connecting initial conditions to final outcomes. Population 3 stars remain hypothetical. These first-generation stars, composed purely of primordial elements, should have been massive, hot, and short-lived. Their deaths would have seeded the universe with its first heavy elements. Despite extensive searches, no confirmed population 3 star has been detected. They might have all died billions of years ago, or we might not recognize their signatures. Upcoming telescopes might finally spot these elusive objects, or at least their characteristic spectral features in the light of distant galaxies. The faint end of the galaxy luminosity function holds crucial information. Numerous small, dim galaxies might collectively contribute more to cosmic history than a few bright ones. These dwarf galaxies could have driven reionization, produced significant stellar mass, and served as building blocks for larger systems, but their faintness makes them difficult to detect and study. Only the deepest surveys with the most sensitive instruments can census these populations. Each new deep field reveals more faint galaxies than the previous one, suggesting even deeper observations will uncover additional populations. Understanding galaxy formation connects to fundamental physics. The process depends on gravity, thermodynamics, nuclear reactions, electromagnetic interactions, and the mysterious properties of dark matter and dark energy. Studying how galaxies form tests our understanding of these physical principles in extreme conditions. Discrepancies between predictions and observations might reveal new physics or force refinements to existing theories. The early universe continues revealing surprises, each observation adding detail to a story billions of years old. Gravitational lensing magnifies these distant targets. When massive galaxy clusters sit between us and early galaxies, their gravity warps space-time, bending and amplifying light from background sources. This natural telescope effect can boost brightness by factors of 10 or more, bringing otherwise invisible objects into view. Einstein predicted this phenomenon, but only modern instruments exploit it systematically. Surveys scan for lensed arcs, distorted images of distant galaxies stretched around foreground clusters. By modeling the lens geometry, astronomers reconstruct the true properties of magnified sources. Some of the faintest early galaxies known were discovered this way. Their light boosted enough to enable detailed spectroscopy and reveal chemical compositions, stellar populations, internal motions. Dust complicates interpretations. Even in young galaxies, dust grains formed from metals can absorb ultraviolet and visible light, re-emitting it in infrared wavelengths. This shifts energy across the spectrum, potentially hiding star formation from optical telescopes while making galaxies brighter in infrared. Early estimates of star formation rates sometimes underestimated true values because dust-obscured activity went undetected. Only when infrared surveys complemented optical observations did the full picture emerge. Balancing multi-wavelength data requires careful modeling, accounting for how dust absorbs, scatters, and re-radiates light depending on grain composition, size distribution, temperature, geometry. Mergers and interactions shaped growth. Galaxies rarely evolved in isolation. Close encounters triggered starbursts as gas clouds collided and compressed. Mergers combined stellar populations and dark matter halos, building larger systems from smaller ones. Some mergers were gentle, others violent. The resulting morphologies depended on mass ratios, orbital parameters, gas fractions. Hierarchical assembly models predict frequent mergers early on when galaxies were closer together and the universe denser. Evidence for this comes from irregular morphologies in deep images, tidal tails extending from disrupted systems, elevated star formation rates in interacting pairs. Not every galaxy merged frequently, but mergers contributed significantly to mass assembly, especially for massive ellipticals. Feedback mechanisms regulated growth. Without feedback, gas would have collapsed too efficiently, forming stars faster than observed and depleting reservoirs too quickly. Supernovae inject energy and momentum, heating gas and driving outflows that eject material from galaxies or prevent it from cooling. Active galactic nuclei can produce even more powerful winds, clearing gas from central regions and shutting down star formation. This self-regulation explains why galaxies don't convert all available gas into stars. Observations reveal outflows moving at hundreds of kilometers per second, carrying mass and metals into intergalactic space. The balance between inflows, star formation, and outflows determines a galaxy's evolutionary trajectory. Too little feedback and galaxies become overly massive. Too much, and they remain stunted. Cosmic ionization unfolded over hundreds of millions of years. It wasn't instantaneous. Ionized bubbles formed around early light sources, expanding and eventually overlapping. Neutral regions shrank as ionized ones grew, until the entire intergalactic medium transitioned from mostly neutral to mostly ionized. The timeline and patchiness of this process affect how we observe distant galaxies. Light traveling through neutral regions gets absorbed by hydrogen, suppressing flux bluewood of the Lyman alpha line. This creates a characteristic spectral break called the Gunn-Peterson trough. By measuring where this break appears in galaxy spectra, astronomers infer redshift and the ionization state of intervening gas. The reionization era corresponds to a period when this trough begins appearing, signaling significant neutral fractions along lines of sight. Quasars provided additional reionization sources. These luminous beacons, powered by rapidly accreting supermassive black holes, emit copious ultraviolet and ionizing radiation. While rarer than star-forming galaxies, their intensity allowed them to ionize large volumes. Detecting quasars at high redshift reveals that supermassive black holes existed surprisingly early, raising questions about how they grew so quickly. Did they form from massive seed black holes, perhaps remnants of population 3 stars, or direct collapse objects? Or did smaller seeds grow through sustained accretion and mergers? Observations show quasars present within the first billion years, implying rapid black hole growth and challenging models that assume slow, steady accretion. The role of dark matter remains central. Galaxies form within dark matter halos, invisible structures whose gravity gathers baryonic matter. Halo mass determines potential well depth, influencing how much gas a galaxy can retain and how resistant it is to feedback. Simulations show galaxies forming at halo centers, with stellar mass correlating with halo mass. But the relationship isn't one-to-one. Feedback, environmental effects, and assembly history introduce scatter. Low-mass halos might form dwarf galaxies or remain dark if feedback expels all gas. Massive halos host giant galaxies, but inefficiencies prevent them from converting all available baryons into stars. Understanding this connection requires matching observed galaxy properties to simulated halo populations, a process complicated by uncertainties in both observations and models. Cosmic variance affects conclusions drawn from small survey volumes. A single deep field might sample an overdense region, finding more galaxies than average, or an underdense void, suggesting fewer. Only by surveying multiple independent fields or very large areas can astronomers average out these fluctuations. Early Hubble studies focused on small regions, leading to debates when different fields yielded different galaxy counts. Expanding surveys resolved these tensions, showing that once sufficient volume is covered, results converge. Cosmic variance decreases with survey size, but never vanishes entirely. It's a fundamental limitation arising from the universe's large-scale structure, a reminder that every observation samples a finite piece of an inhomogeneous whole. Spectroscopy confirms distances and reveals properties. Images show galaxy positions and brightnesses, but spectra provide redshifts, chemical abundances, ionization states, stellar ages, star formation rates. Obtaining spectra of faint, distant galaxies requires long exposure times on large telescopes. Multiplex spectrographs observe many galaxies simultaneously, improving efficiency. Spectroscopic surveys systematically target galaxies across wide areas, building datasets that map cosmic structure in 3 dimensions. Redshift measurements place galaxies in cosmic time, allowing studies of evolution. Emission lines reveal active star formation, ionizing radiation, gas metallicity. Absorption lines trace stellar populations and ages. Combining imaging and spectroscopy provides a complete picture, linking what galaxies look like to what they're made of and how they're evolving. Metallicity evolution tracks chemical enrichment. The first stars formed from primordial gas, producing metals that dispersed into surroundings. Subsequent generations incorporated these metals, building progressively enriched populations. Measuring metallicity in distant galaxies reveals how quickly enrichment occurred, how efficiently metals mixed, whether early galaxies were uniformly enriched or chemically heterogeneous. Observations show galaxies at high redshift with lower metallicities than nearby ones, consistent with less time for enrichment. But some early galaxies display surprisingly high metallicities, suggesting rapid star formation and efficient mixing. Scatter in metallicity at fixed stellar mass indicates diversity in star formation histories, gas accretion rates, outflow efficiencies. Tracking metallicity evolution constrains models of stellar feedback, gas recycling, intergalactic medium enrichment. The stellar initial mass function might have varied early on. Today, star formation produces a characteristic distribution of stellar masses, with more low-mass stars than high-mass ones. But under different conditions, this distribution might shift. Lower metallicity, higher temperatures, or different turbulence could favor massive stars. If the initial mass function was top-heavy in early galaxies, more high-mass stars formed, producing more ultraviolet light, more supernova feedback, and different chemical yields. Observations testing this idea look for signatures in integrated spectra, supernova rates, or nucleosynthetic patterns. Evidence remains mixed. Some studies suggest variations, others find consistency with the local initial mass function. Resolving this question impacts estimates of star formation rates, feedback strengths, and metal production in the early universe. Galaxy morphologies transition from irregular to ordered. Early galaxies often appear clumpy, asymmetric, lacking the smooth disks or elliptical profiles seen nearby. This reflects their chaotic formation, ongoing mergers, clumpy star formation driven by gravitational instabilities. As galaxies aged, they settled into more regular shapes. Disk galaxies formed from gas settling into rotating structures. Ellipticals resulted from mergers that randomized stellar orbits. Morphological evolution traces dynamical processes, gas accretion, merger histories. Quantifying morphology at high redshift is challenging because galaxies are small, faint, and often blurred by atmospheric seeing or instrumental resolution. Space telescopes provide clearer views, revealing detailed structures. Statistical studies classify thousands of galaxies, tracking morphological distributions across cosmic time. Environmental effects influenced evolution. Galaxies in dense clusters experienced ram pressure stripping as they moved through hot intracluster gas, removing cold gas and quenching star formation. Tidal interactions with neighbors triggered starbursts or disrupted structures. Isolated field galaxies evolved more quiescently, retaining gas and forming stars steadily. The fraction of galaxies in clusters versus field environments changed over time as large-scale structure grew. Early on, fewer massive clusters existed, so environmental effects were less pronounced. Observations show higher star formation rates in field galaxies at high redshift compared to cluster galaxies, consistent with environmental quenching. Understanding these effects requires comparing galaxy properties across different environments at multiple epochs. Stellar mass functions quantify galaxy populations. Plotting the number of galaxies per unit volume versus stellar mass reveals the mass distribution. This function evolved over time as galaxies formed, grew through star formation and mergers, or were disrupted. The low mass end counts numerous dwarf galaxies, the high mass end rare giants. Measuring the stellar mass function at different redshifts traces mass assembly. The total stellar mass density increased as gas converted into stars. The shape evolved as different mass ranges grew at different rates. Massive galaxies assembled earlier than expected in some models, a puzzle dubbed downsizing, where the most massive systems completed star formation first, contrary to hierarchical expectations. Cosmic star formation rate density peaked around redshift 2. Integrating star formation rates across all galaxies at a given epoch gives the cosmic star formation rate density, a measure of how actively the universe was forming stars. This quantity rose from early times, peaked several billion years after the Big Bang, then declined toward the present. The peak corresponds to an era when gas was still abundant, galaxies were actively assembling, and feedback hadn't yet shut down star formation in massive systems. Understanding this history reveals how efficiently the universe converted primordial gas into stars, how feedback and gas accretion balanced, how the transition from an active to a quiescent universe occurred. The first billion years set the stage for everything that followed. Structures formed, chemical elements dispersed, black holes grew, galaxies assembled. The universe transitioned from a simple, homogeneous state to a complex, structured cosmos. Studying this epoch reveals fundamental processes governing cosmic evolution. Each new observation refines our understanding, filling gaps in a story written across billions of years. The journey from the first light to the present continues unfolding, driven by curiosity, advanced technology, and the quiet persistence of scientists decoding faint signals from the universe's distant past. Observational constraints tighten theoretical models. Every measurement, every spectrum, every image provides data that theories must explain. When observations conflict with predictions, models adjust. This iterative process refines our understanding, narrowing possibilities, eliminating incorrect assumptions. Early cosmological models predicted galaxy formation timescales that observations contradicted. Massive galaxies appeared too early, too structured. Models incorporated additional physics, faster gas cooling, more efficient star formation in dense environments, revised feedback prescriptions. Each adjustment brought simulations closer to reality. Observational programs target specific questions. Surveys designed to measure galaxy clustering at high redshift test dark matter models. Spectroscopic campaigns measuring chemical abundances constrain nucleosynthesis and enrichment histories. Imaging programs tracking morphological evolution reveal merger rates and structural transformations. These coordinated efforts build comprehensive data sets, enabling statistical analyses that individual observations cannot provide. Large collaborations manage these projects, pooling resources, expertise, data. The synergy between observation and theory drives progress. Neither alone suffices. Observations without theoretical framework remain unexplained patterns. Theories without observational tests remain speculation. Together, they construct a coherent narrative of cosmic history. Dark matter's role remains central, yet mysterious. Its gravitational influence shaped structure formation, determined galaxy masses, influenced rotation curves. Yet, its particle nature eludes detection. Laboratory experiments search for dark matter interactions with ordinary matter, attempting direct detection. Particle accelerators seek to produce dark matter particles, testing hypotheses about their properties. Astrophysical observations constrain dark matter's distribution, behavior, interaction cross-sections. Despite decades of effort, no definitive detection has occurred. This absence challenges physicists, prompting alternative theories. Modified gravity models propose changes to gravitational laws at large scales, attempting to explain observations without invoking unseen matter. These alternatives face difficulties explaining multiple independent observations consistently. Dark matter models remain favored because they naturally account for diverse phenomena. Galaxy rotation curves, cluster dynamics, gravitational lensing, cosmic microwave background anisotropies, large-scale structure formation. The convergence of evidence from independent methods strengthens confidence in dark matter's existence, even as its fundamental nature remains unknown. Future experiments may finally identify the particle, revealing whether it's a weakly interacting massive particle, an axion, a sterile neutrino, or something entirely unexpected. Until then, dark matter remains the universe's most abundant, yet most elusive component. Ryonization's details continue unfolding. The transition from neutral to ionized hydrogen spanned hundreds of millions of years, a gradual process rather than instantaneous event. Early galaxies began ionizing their surroundings, creating expanding bubbles of ionized gas. These bubbles grew, overlapped, eventually merging into a fully ionized intergalactic medium. The topology of reionization, how these bubbles distributed and connected, remains uncertain. Simulations model this process, predicting bubble sizes, growth rates, ionization fractions at different epochs. Observations test these predictions by measuring neutral hydrogen absorption in quasar spectra, detecting ionized regions around early galaxies, mapping large-scale ionization patterns. The timing of reionization's completion, around redshift 6, is constrained by multiple observations. Earlier epochs show increasing neutral fractions, indicating incomplete reionization. Later epochs show fully ionized conditions. The transition's duration, roughly from redshift 15 to 6, reflects the gradual buildup of ionizing sources and the patchy nature of ionization. Understanding reionization requires knowing the ionizing photon production efficiency of early galaxies, the escape fraction of photons from galaxies into the intergalactic medium, the clumpiness of the intergalactic medium affecting recombination rates. Each factor influences the timeline and topology. Observations of high redshift galaxies with James Webb Space Telescope provide new constraints, measuring star formation rates, stellar populations, ionizing photon production. These data feed into models, refining predictions, testing assumptions. Reionization represents a critical phase transition, fundamentally altering the universe's physical state, enabling subsequent structure formation and evolution. Chemical evolution tracks stellar life cycles. Stars form from gas, fuse elements, then return enriched material to the interstellar medium via stellar winds, supernova explosions, planetary nebulae ejection. This cycle enriches successive generations, gradually increasing heavy element abundances. Observing abundance patterns in stars of different ages reveals this history. Old stars, formed early, show low metallicities, reflecting the universe's initial composition. Younger stars display higher metallicities, incorporating products of earlier stellar generations. Abundance ratios provide additional information. Alpha elements like oxygen, neon, magnesium are produced in massive stars and released in core collapse supernovae. Iron is produced in type 1a supernovae, which occur on longer timescales. The alpha to iron ratio traces star formation history and supernova rates. High alpha to iron ratios indicate rapid star formation dominated by massive stars. Lower ratios suggest slower star formation, allowing type 1, a supernovae, to contribute. Observing these ratios in galaxies at different redshifts and environments reveals how star formation histories varied. Dwarf galaxies often show different abundance patterns than massive galaxies, reflecting different star formation efficiencies, gas retention, and enrichment timescales. Chemical evolution models incorporate stellar yields, initial mass functions, star formation rates, gas inflows and outflows. Matching models to observations constrains these parameters, revealing how efficiently galaxies converted gas into stars, how feedback regulated enrichment, how gas accretion diluted or enhanced metallicities. The chemical fingerprints in starlight tell stories of stellar births, deaths, and the recycling of cosmic material. Galaxy scaling relations reveal fundamental physics. Relationships between galaxy properties, such as the Tully-Fisher relation, linking rotation velocity and luminosity, or the fundamental plane-relating size, velocity dispersion, and surface brightness, encode information about formation processes. These relations hold across wide ranges, suggesting underlying physical principles governing galaxy structure. Dark matter halos influence these relations through gravitational potential. Baryonic processes like star formation and feedback shape observable properties. The tightness of scaling relations indicates that despite diverse formation histories, galaxies settle into predictable configurations. Deviations from these relations signal unusual histories, interactions, or environmental effects. Studying scaling relations at high redshift tests whether they hold universally or evolve over time. Some relations show evolution, indicating that galaxy properties changed as the universe aged. Others remain remarkably stable, suggesting that fundamental processes remained consistent. Understanding why certain relations hold and others evolve constrains galaxy formation theories. Simulations reproduce these relations by adjusting baryonic physics prescriptions, testing which mechanisms produce observed trends. Scaling relations provide benchmarks, simple tests that complex models must pass. Their existence and evolution offer windows into the interplay between dark matter, gas dynamics, star formation, and feedback across cosmic time. Supermassive black holes co-evolved with galaxies. Observations reveal correlations between black hole masses and host galaxy properties, such as bulge mass or velocity dispersion. These relationships suggest that black hole growth and galaxy evolution are linked, despite the vast difference in scales. Feedback from accreting black holes through jets and radiation can heat or expel gas, regulating star formation. This feedback may explain why the most massive galaxies have lower star formation rates than expected. The co-evolution implies that black holes and galaxies influenced each other's growth. Mergers brought black holes together, triggering accretion and fueling quasar activity. Quasars, in turn, injected energy into their surroundings, affecting subsequent star formation. Tracing this co-evolution requires measuring black hole masses across cosmic time, tracking quasar activity, and correlating these with galaxy properties. High redshift quasars indicate that supermassive black holes formed early, sometimes before their host galaxies fully assembled. How black holes grew so rapidly remains debated. Direct collapse from primordial gas, super Eddington accretion, or mergers of intermediate mass black holes are proposed mechanisms. Each has different observational signatures. Gravitational wave D, detections of merging black holes provide new insights, revealing populations and merger rates. The interplay between black holes and galaxies shaped the universe's large-scale structure, regulating where and when stars formed, influencing galaxy morphologies, and leaving imprints in the cosmic web's distribution of matter. Cosmic variance complicates high redshift studies. The observable universe contains finite volume, and at high redshift, the surveyed volume shrinks. Small survey areas may not represent the average universe due to statistical fluctuations in structure distribution. This cosmic variance introduces uncertainty in measurements, making it challenging to determine whether observed properties are typical or outliers. Large surveys mitigate this by covering wider areas, averaging over more structures. Deep pencil beam surveys, though reaching faint objects, suffer from small volumes and high cosmic variance. Balancing depth and area is crucial for robust statistical conclusions. Simulations help quantify cosmic variance by modeling structure formation and predicting fluctuations in observed quantities. Comparing observed distributions to simulated predictions reveals whether results are consistent with expectations or indicate new physics. Cosmic variance affects number counts, luminosity functions, clustering measurements. Accounting for it requires careful statistical analysis, often incorporating simulations to estimate uncertainties. As surveys expand, cosmic variance decreases, improving constraints on galaxy properties and cosmological parameters. Understanding cosmic variance is essential for interpreting high redshift observations, distinguishing genuine evolution from statistical noise, and ensuring that conclusions about the early universe rest on solid statistical foundations. Dust obscuration hides star formation. Dust grains absorb ultraviolet and optical light from young stars, re-radiating energy in the infrared. This obscuration makes star-forming regions appear dimmer in optical wavelengths, leading to underestimated star formation rates if only optical data are used. Infrared observations reveal hidden star formation, uncovering luminous infrared galaxies and ultraluminous infrared galaxies undergoing intense starbursts. Combining optical and infrared data provides complete pictures of star formation. Dust corrections apply to measurements, accounting for extinction and reprocessing. The amount of dust varies between galaxies, depending on metallicity, star formation history, and geometry. Low metallicity galaxies have less dust, making optical observation more reliable. High metallicity, gas-rich galaxies can be heavily obscured, requiring infrared observations. Sub-millimeter observations detect the coldest dust, tracing molecular gas reservoirs fueling star formation. These observations reveal populations of dusty star-forming galaxies at high redshift, contributing significantly to cosmic star formation rate density. Understanding dust's role requires modeling its properties, distribution, and interaction with radiation. Dust models incorporate grain sizes, compositions, temperatures, predicting emission spectra, and extinction curves. Matching models to observations constrains dust masses, star formation rates, and galaxy structures. Dust is not merely an observational nuisance. It plays active roles in cooling gas, shielding molecules, and influencing star formation. Accounting for dust transforms our view of galaxy evolution, revealing hidden activity and refining star formation histories. Gravitational lensing magnifies distant objects. Massive foreground structures, like galaxy clusters, bend light from background sources, creating magnified, distorted, or multiple images. This natural telescope effect allows observation of faint, distant galaxies otherwise undetectable. Lensing boosts sensitivity, enabling studies of intrinsically faint objects at high redshift. Lensed galaxies appear brighter, larger, facilitating spectroscopy and detailed imaging. Lensing also provides mass measurements of foreground lenses, independent of light, constraining dark matter distributions. Strong lensing produces dramatic arcs and multiple images. Weak lensing causes subtle shape distortions measurable statistically. Both probe mass distributions, testing cosmological models, and structure formation theories. High redshift galaxies discovered behind lensing clusters reveal early galaxy populations, providing insights into their properties, sizes, star formation rates, and chemical compositions. Lensing surveys systematically search for lensed objects, building samples for statistical studies. Lensing models reconstruct source properties from observed images, accounting for magnification and distortion. This technique has uncovered some of the most distant galaxies known, pushing observational limits. Lensing is a powerful tool, leveraging gravity itself to explore the universe's earliest epochs, complementing direct observations and expanding the accessible cosmic volume. Stellar populations encode histories. Stars within galaxies span ages, metallicities, and masses, reflecting formation and enrichment histories. Analyzing integrated light from galaxies reveals stellar population properties through spectral features. Absorption lines indicate temperatures, surface gravities, chemical abundances. Stellar population synthesis models predict spectra based on star formation histories, metallicities, ages. Fitting models to observed spectra infers these parameters, reconstructing how galaxies assembled stars over time. Old stellar populations dominate red, passive galaxies, indicating early star formation that subsequently ceased. Young populations dominate blue, star-forming galaxies, showing ongoing activity. Intermediate age populations suggest recent starboom, RSTs, or gradual buildup. Disentangling age and metallicity is challenging because both affect spectra similarly. High-resolution spectroscopy and multi-wavelength data break degeneracies, improving constraints. Stellar population studies at high redshift face difficulties due to faintness, requiring long exposures and sensitive instruments. James Webb Space Telescope's infrared capabilities enable detailed stellar population analyses of distant galaxies, revealing ages and metallicities previously inaccessible. Understanding stellar populations connects observable galaxy properties to underlying formation processes, tracing how gas converted into stars, how feedback and mergers influence star formation, and how galaxies transitioned between active and quiescent states. Stellar populations are archaeological records, preserving information about events long past, readable through careful spectroscopic analysis. Feedback mechanisms regulate galaxy growth. Star formation and black hole accretion release energy, driving winds that expel gas, heat surrounding material, and suppress further activity. Without feedback, galaxies would convert gas into stars too efficiently, producing overly massive galaxies inconsistent with observations. Feedback explains why star formation is inefficient, why galaxies lie below naive expectations. Supernova-driven winds from massive stars inject energy and momentum into the interstellar medium, creating bubbles, driving outflows. Active galactic nuclei feedback from accreting black holes, heats gas via radiation, jets, or winds, preventing cooling and star formation. These processes are challenging to model because they span vast spatial scales, from stellar to galactic, and involve complex physics. Simulations implement feedback prescriptions, tuning parameters to match observations. Different feedback models produce different outcomes, affecting galaxy masses, star formation rates, morphologies. Observations constrain feedback by measuring outflow velocities, mass loss rates, and correlations between star formation and gas content. Detecting outflows requires spectroscopy revealing blue-shifted absorption lines or emission from shocked gas. Feedback is essential for realistic galaxy formation models, transforming theoretical predictions from inconsistent with observations to remarkably accurate. Understanding feedback's efficiency, timing, and impact remains a frontier, with implications for galaxy evolution, chemical enrichment, and the fate of baryons across cosmic time. Human ingenuity drives discovery. Every observation, simulation, and theory represents collective effort, generations of scientists building on predecessors' work. The journey from noticing fuzzy patches in telescopes to mapping the universe's first billion years reflects persistence, creativity, technological innovation. Instruments improve, theories refine, questions evolve. Each answer raises new questions, pushing boundaries further. The universe's story unfolds through collaboration, shared data, open inquiry. Mistakes are made, corrected, and learned from. Unexpected discoveries redirect research, opening unanticipated avenues. The process is iterative, incremental, occasionally punctuated by breakthroughs. Understanding the first billion years required developing quantum mechanics, general relativity, nuclear physics, computational methods, detector technologies. It required imagining processes never directly witnessed, inferring histories from faint light, trusting mathematics to describe reality. The quest continues, driven by curiosity about origins, existence, and our place in the cosmos. The first billion years set the stage, but the story extends forward and backward, connecting past, present, and future. Each discovery adds pieces to an ever-expanding puzzle, revealing a universe more intricate, dynamic, and wondrous than previously imagined. The exploration persists, fueled by the quiet determination to understand everything. The quest to understand the first billion years extends beyond mapping events. It demands explaining why structures formed when and where they did, why some galaxies evolved differently than others, why the universe transitioned from darkness to light in precisely the manner observed. Cosmological parameters set initial conditions, determining expansion rate, density fluctuations, dark matter abundance. Small variations in these parameters produce dramatically different universes. If dark matter interacted more strongly, structures would form earlier or collapse differently. If dark energy dominated sooner, expansion would accelerate before galaxies assembled. The universe's parameters appear finely tuned, enabling the complexity we observe. Whether this reflects fundamental physics, anthropic selection, or deeper principles remains debated. Precision measurements constrain parameters, reducing uncertainties. cosmic microwave background observations fix values to percent-level accuracy. Combining multiple probes, supernovae, baryon acoustic oscillations, gravitational lensing, breaks degeneracies, tightening constraints. Yet tensions emerge. Different methods sometimes yield inconsistent values, particularly for Hubble constant and matter density. Resolving these tensions might require new physics or systematic errors in measurements. The early universe provides independent constraints, testing consistency across cosmic time. If parameters from recombination differ from local measurements, something is misunderstood. Reconciling observations across epochs sharpens understanding, revealing whether standard models suffice or modifications are necessary. Dark matter remains enigmatic. Its gravitational effects are unmistakable. Galaxies rotate faster than visible matter allows. Clusters hold together despite insufficient baryonic mass. Gravitational lensing reveals mass distributions inconsistent with light. Yet its identity eludes discovery. Particle physics proposes candidates: weakly interacting massive particles, axions, sterile neutrinos, but direct detection experiments have not confirmed any. Indirect searches look for annihilation or decay signatures, scanning for excess gamma rays or cosmic rays. Collider experiments attempt producing dark matter particles, constraining properties through absence of signals. The lack of detection narrows possibilities but doesn't eliminate candidates. Perhaps dark matter interacts even more weakly than assumed, or its mass lies outside explored ranges. Alternative theories modify gravity itself, proposing that gravitational laws differ on galactic scales. Modified Newtonian dynamics and related frameworks reproduce rotation curves without dark matter, but struggle explaining other observations like cosmic microwave background and large-scale structure. Most cosmologists favor dark matter paradigm due to its explanatory power, but the mystery persists. Understanding dark matter's nature would revolutionize physics, connecting cosmology, particle physics, and fundamental forces. The first billion years provides crucial tests. Dark matter's properties affected structure formation timing, halo masses, and galaxy assembly. Observations of high redshift galaxies constrain dark matter models, ruling out candidates inconsistent with early structure formation. Solving this puzzle requires breakthroughs in detection technology, theoretical insights, or serendipitous discoveries. Ionization's patchiness reflects underlying structure. The process didn't occur uniformly. Dense regions ionized first, creating ionized bubbles that expanded, merged, and eventually percolated across space. Observations reveal this inhomogeneity through variations in spectra of distant quasars and galaxies. Neutral hydrogen absorbs specific wavelengths, creating absorption features. When ionization is incomplete, absorption patterns vary depending on sightline, indicating patchy ionization. Statistical analyses measure bubble sizes, ionized fractions, and topology. These measurements constrain re-ionization models, distinguishing scenarios dominated by numerous faint galaxies from those driven by rare bright sources. Simulations predict bubble growth, comparing morphology and timing against observations. Disagreements highlight missing physics or incorrect assumptions. Current data suggest reionization completed around redshift 6, but uncertainties remain regarding its start, duration, and driving sources. Future observations will map ionization fields in 3 dimensions, revealing how bubbles grew and merged. This detailed picture will identify sources responsible, whether massive stars and galaxies, accreting black holes, or exotic phenomena. Understanding reionization's topology connects small-scale processes, star formation, feedback, to large-scale outcomes, ionization fields, cosmic web illumination, It bridges micro and macro, showing how local events propagate, influencing the universe globally. Observations continue refining this picture, each dataset adding resolution. James Webb reveals galaxies at redshifts once thought unreachable, their light stretched across billions of years. Spectroscopy dissects that light into components, measuring velocities, temperatures, compositions. Imaging captures morphologies, sizes, structures frozen in cosmic time. Together, these tools reconstruct histories spanning eons, transforming photons into narratives. The process demands patience, precision, collaboration across disciplines and continents. Data archives preserve findings, enabling meta-analyses that extract patterns invisible in individual studies. Open access policies democratize knowledge, allowing researchers worldwide to test hypotheses, challenge conclusions, and propose alternate lives. Science advances through this collective scrutiny, converging toward truth through debate and evidence. The first billion years shaped everything afterward. Initial density fluctuations, amplified by gravity, determined where galaxies formed. Early star formation seeded space with metals, enabling later generations. Black holes grew from seeds planted then, influencing galaxy evolution across epochs. Feedback established cycles of star formation and quenching that persist today. The cosmic web's architecture, laid down early, guides matter flows and galaxy interactions billions of years later. Understanding this formative period explains not just ancient history, but ongoing processes. Modern galaxies carry imprints of their origins, detectable in stellar populations, chemical abundances, and structural features. By studying the present, we infer the past. By observing the past, we understand the present. Each discovery prompts deeper questions. Finding galaxies earlier than expected challenges formation timescales. Detecting massive black holes so soon after the Big Bang demands explanations. Observing mature structures when chaos seemed inevitable suggests missing physics. These puzzles drive research forward, ensuring that complacency never settles. The universe refuses simplicity, offering complexity at every scale. What appears understood often conceals subtleties requiring refinement. Models that matched yesterday's data may fail tomorrow's observations. This iterative refinement, frustrating yet exhilarating, defines scientific progress. We build understanding incrementally, each generation standing on predecessors' shoulders, seeing slightly farther. The tools improve relentlessly. Telescopes grow larger, detectors more sensitive, algorithms smarter. Computational power increases, enabling simulations of unprecedented resolution. Machine learning identifies patterns in massive data sets, accelerating discovery. International collaborations pool resources, constructing facilities no single nation could afford. The pace accelerates, but fundamental challenges remain. Distance limits observation, light takes time to travel, and faint signals hide in noise. Yet ingenuity finds ways. Gravitational lensing magnifies distant objects. Statistical methods extract signals from backgrounds. Multi-wavelength approaches reveal hidden phenomena. Each technical advance unlocks new cosmic volumes, pushing boundaries outward and backward. The first billion years will never be directly witnessed. We observe remnants, echoes, and consequences. The universe doesn't preserve records in archives we can browse. Instead, it encodes history in light, matter distributions, and chemical fingerprints. Decoding these requires inference, modeling, and testing hypotheses against observations. Certainty remains elusive, but confidence grows as independent methods converge. When spectroscopy, imaging, simulations, and theory agree, trust builds. When contradictions emerge, investigations deepen until resolutions surface. This process, neither fast nor guaranteed, produces knowledge robust enough to withstand scrutiny. The story extends beyond science into philosophy. Why does the universe exist? Why these physical laws? Why this particular history? Science addresses how, not why, describing processes without invoking purpose. Yet the elegance of physical laws, the emergence of complexity from simplicity, the universe's capacity for self-awareness through conscious beings, these invite wonder. The first billion years transformed quantum fluctuations into galaxies, stars, and eventually life. That transformation, governed by physics yet staggering in scope, connects us to cosmic origins. We are made of star-forged elements, products of processes initiated when the universe was young. Understanding our origins situates us within the cosmos, not as separate observers, but as participants in its unfolding. Future observations will sharpen this picture further. Next-generation telescopes will detect even earlier galaxies, constraining the absolute beginning of structure formation. Improved spectroscopy will measure faint emission lines, revealing properties currently inaccessible. Larger surveys will reduce cosmic variance, enabling statistical analyses of rare populations. Gravitational wave astronomy will detect merging black holes across cosmic time, tracing their growth and prevalence. Neutrino detectors might capture signals from the first supernovae, providing independent probes of early stellar populations. Each new capability opens windows previously closed, revealing aspects of the early universe hidden from current instruments. The narrative will continue evolving. Today's consensus may become tomorrow's outdated model. Observations might reveal phenomena requiring entirely new frameworks. Dark matter could be identified, rewriting structure formation theory. Dark energy's nature might be uncovered, explaining cosmic acceleration. Quantum gravity theories could connect cosmology to fundamental physics, explaining initial conditions. Or mysteries might deepen, revealing layers of complexity currently unimagined. Either outcome advances understanding. Solving puzzles provides closure and new foundations. Discovering deeper mysteries sustains curiosity and drives exploration. The universe offers both, solutions that satisfy and questions that inspire. The first billion years taught the universe how to build. From featureless beginnings emerged structure, hierarchy, and complexity. Gravity organized matter into filaments, halos, and galaxies. Nuclear fusion ignited stars, producing light and heavy elements. Feedback regulated growth, preventing runaway processes. Mergers combined small structures into larger ones. Black holes grew, influencing surroundings through energy and momentum. Chemistry diversified, enabling molecules, dust, and eventually planets. Life arose somewhere, somehow, transforming chemistry into biology. Each step built upon previous ones, increasing complexity through physical processes. The early universe set this trajectory, establishing conditions that allowed subsequent developments. Understanding that beginning illuminates the path leading to now. The exploration continues, driven not by necessity, but by curiosity. Practical applications are few. Knowing the first galaxy's properties doesn't change daily life. Yet the pursuit matters. It satisfies deep human desires to understand origins, context, and place in the cosmos. It demonstrates what collective effort achieves, transcending borders, languages, and generations. It inspires wonder at the universe's scale, age, and intricacy. It reveals that reality exceeds imagination, that nature's creativity surpasses human invention. The first billion years offers a story of transformation, from simplicity to complexity, darkness to light, formless potential to structured reality. That story, still being written by researchers worldwide, connects past to present, physics to philosophy, and data to meaning.